we actually covered the Laplace domain, no, the time domain in the last lecture. So we talked about system dynamics. So this is actually the first big part we are covering, right? Where we talk about system and how can we generally describe them in the time domain. So we use ODEs. We have a very special case. We have linear ODEs, time invariant ones, and so on. If they are linear and time invariant, I'm going to recap that in a slide in a second, we can actually move over to the Laplace domain. So why is this even useful? Well, this is useful because it makes actually our life easier. So the thing is, for students, when we start working in the Laplace domain, it does not appear that it makes your life easier, because it's a pretty hard abstraction of what you're doing. So as a mechanical engineer, we are used to knowing that, okay, if we have a function of time, we know what's going on. Now we're going to have a function of s, so the famous Laplace variable. So what does that even mean? So it's kind of a switch you need to turn in your head, and unfortunately, it always takes some time. So really, don't be scared at the beginning when you have a hard time to understand. Everybody has, right? When I started learning control, learning to understand systems in the Laplace domain, it also took some time on this, until this coin basically flipped in the head. But suddenly you will come to a conclusion, okay, now I got it, right? But it takes 1 or 2 lectures. Okay, so this statement, I had a lot of discussion about that, because my students who are doing bachelor thesis with me, they said, actually, I should tell this, that when you do Laplace and start with control, it's sometimes at the beginning hard to understand, but there comes the point where you simply get it, right? But it's not there from the beginning, like when you do other subjects. So this time, I'm telling you, in the last semesters, I did not tell, and I'm trusting the students here, right? They said it's a good idea to be open at the beginning and say, okay, it's a little bit strange at the beginning. Okay, that's basically it. Otherwise, there's not much more to say, right? So we covered a couple of examples last time, so we are ready to jump in. We move now from the time to the Laplace domain. And today is basically some basic principles and some motivation, why we're actually doing this in controls to work in the Laplace domain and not in the time domain. And I will try to motivate that story a little bit. So let's move over to our presentation. Okay, dynamical systems in the Laplace domain. So instead of our beloved ODEs, right, where we had something like this, for example, we're gonna move over to the Laplace domain, and we're gonna work with so-called transfer functions. So you see, instead of the dependence of t, you then have a dependence on this Laplace variable s. And I will show you why this is important and how you actually can do that. The important stuff is here on this first slide, that it is, our transfer function in the Laplace domain is an equivalent representation. So we are not losing any, well, we are actually losing a bit of information, but it's not really a problem. So it's basically going to the Laplace domain, it's an equivalent representation. So all the information we need is there, right? It's just writing, so to say, our system in a different form, in a different space, right? In the Laplace domain, in a different domain, not space. So it's, however, everything what we have as information in our ODE in the time domain, we're going to have that information in the Laplace domain. So this is one key assumption, key point you should always bear in mind. We are not moving to something else and we lose half the information. It's really just rewriting the equation and have a different mathematical concept behind. However, our information is there, right? And this is important, especially for us as engineers, right? We want to fly the aircraft. We have a mathematical description in the time domain. We move that description over to a different domain, in the Laplace domain. All the information, how fast the aircraft is flying, is the aircraft stable, the station or the final value gain and so on, they should all be the same, right? And this holds for the Laplace domain, so we don't lose anything. Okay, so let me start with the following. We are dealing here with linear time invariant systems. They are shortly called LTI. In German, you would call them LZI for linear zeitinvariante Systeme. Most of the time, also the German, or often the German literature also uses LTI. So why is it important that we have these two features? Well, we've learned about these two features, right? When we started out with the ODEs. So let's recap, and then we're going to say why they are important. If you remember, linearity. What does a linear system define? A system is called linear if the system responds to two linear superimposed input signals equally linear superimposed at the output, superposition principle, right? So this is what we call a superposition principle. I've presented you this statement here, so to say, already once. The important stuff is here really when you have a system, let's call it G, you feed in some input Y and you measure you feed in some input U1 and you measure the output Y1, and then you take the very same system and feed in another input and you measure the output. If and only if the system is linear, you actually can add these two inputs together and you will end up with a signal which is composed of the two outputs, right? So this only holds for linear system, right? So this is important. It's just a recap what a linear system is and what it's defined for. So time invariant, well, time invariant means simply that you have a system which is not dependent when you start it, right? So think of the espresso machine, right? If it's modeled, it does not matter if you press in Simulink play now or in 1 hour, right? The time itself does not change the result, right? Of course, if you run it, it has some dependence over time, but it's not explicitly dependent on time, meaning that it does not matter if you start it in the morning or in the evening in your MATLAB file, right? That's what a time invariant system is. It does not explicitly depend on time. Okay, so why are recapping this? Well, this is the definition of a linear time invariant system. And it's important to note here, please, it's often mistaken in practice. You're only allowed to move to the Laplace domain if your system is linear and time invariant, right? The Laplace domain is basically a mathematical tool where you kind of do a transformation from the time to the Laplace domain, and you're only allowed to do this when your system is linear and time invariant. If you have a nonlinear system, you cannot do it. It does not hold, right? So this is a prerequisite we have to take into account and should not forget. So obviously, and this is coming back, I think I've mentioned that obviously in reality our systems are nonlinear, right? Every time you're dealing with a system in practice, it will be nonlinear. For example, the espresso machine. Our espresso machine is in a way nonlinear simply because there will be a maximum power we can put into our espresso machine. If you take a wind turbine and take 2 megawatts and plug it into your espresso machine, it's gonna be a problem, right? It's gonna blow up probably. So it's not going to linear. Linearity means if you double the input, you would double, for example, the output, right? Obviously, there in practice are constraints. Think of your car, right? If you go, there's a limitation that you have 100% gas pedal position. You cannot do more, so you cannot double the output. So this would be a nonlinear constraint. So, however, as engineers, we do like approximations because they make our life easier, and we are often going to say, our system behaves kind of like a linear system, so why not work with the linear system, right? Because it makes our life much easier, because we know when we have linear systems, they are much easier to solve, they are much easier to work with. But as an engineer, you always have to bear in mind that your system in practice will be nonlinear. And for those of you who might work later in control will figure out that pretty quickly that you cannot demand arbitrary power from your espresso machine, or you cannot heat up the water in your espresso machine to 1000 degree, right? Your system is linear. There are constraints. However, working with a linear system, making our lives easier, is usually a valid approach. But when we then go into practice, we always have to bear in mind that there are limitations, right? So, okay, the whole Laplace domain only holds if our system is linear. So if you say you want to work in a Laplace domain for your given system, for your aircraft, you have to approximate with a linear ODE. Okay, so this was kind of the prerequisite in the when we are allowed to do it. But now I actually want to show you a little bit of motivation. I hope you're not fed up with this example already. It's a simple spring mass damper oscillator. And for that system, we know how the second order ODE looks like, right? So everybody of you should realize that this is a PT2 system because we have a proportional part and we have a second order lag in there. Okay, so what is actually the problem with this system? Well, actually, there's no problem, right? We know how to solve it. But now let's think about it, how you would solve it if I say, please compute it for a step response. You could say, okay, I'm going to MATLAB and I'm coded and it's going to be solved numerically. Fair enough, I'd say. But one thing is, if we solve, let's assume we don't have MATLAB and we want to solve that on paper. We're going to go with the homogeneous solution. So we're going to say, okay, our input is 0 and we solve for the eigenmotion. We know if the system is stable, if it's oscillating and so on. We know that by the eigenvalues, right? So, and the second part is we are solving the particulate solution. So what's the problem with the particulate solution? The particulate solution is solved for a specific input, right? Remember the PD1 we solved on paper? We said, okay, the input is going to be a step. So now you could say, I don't want to define the input. I just want to solve it for an arbitrary input, for any input. So for U of t, and U of t can be anything. Obviously, you will immediately see that's not possible. You can write the solution y of t there, but you will still have an integral there. And what you're left with is the so-called convolutional integral, right? In German, Faltungsintegral, right? So when you write down your y of t and don't define your input, you don't say it's a step, it's an impulse, it's a ramp. You just say u of t can be anything. Then you have a solution which is basically not calculated until the end, but you can write the solution there. But what shows up is the convolutional integral. So you're stuck, right? So you cannot go any further until you solve, you define the input. And this is kind of a problem for us as engineers, because maybe we want to know certain things, how the system is reacting to a certain input. So is there a way to get more information out of this without actually solving this convolutional integral? Because nobody of you and me likes to solve convolutional integrals, right? And this is the main motivation for the Laplace domain. We can move our ODE over to a different domain where we can immediately get out a lot of information without actually solving the integral, right? Without actually solving the particulate solution. Or differently, solving it in the Laplace domain is much easier because we don't need to solve it. We just need to use basic algebraic computation like plus, minus, multiplication, and divisions. So we are moving away from differential and integral equations to actually simple rational functions, which we can use our basic knowledge from high school, right? Multiply, plus, and so on. So this is the actual motivation why we want to do this and why we're going to take the twist in our head to move away from the time domain. Okay, so to obtain y of t for any, you could say not only any, but an arbitrary. So any u of t, right? the ODE must be solved. But if you don't define u of t to be a certain input, it's going to lead to the convolutional integral. And this is kind of, yeah, as I said, we don't like to solve these integrals because they can get very complex if your input gets very complex. For a step, it's usually okay. Okay, so this was the motivation. And actually, this was already the spoiler. The spoiler was, if we move to the Laplace domain, we know it makes our life easier because instead of a differential equation, we will have a rational function where we can work pretty easy with it, and there are certain rules we can apply, and we can get out a lot of information of our system behavior without actually solving the integral. Right? So it has something to do with the eigenvalues, of course, but also for a certain input. Right? Okay, so next thing, we're going to do a kind of a mind experiment. Don't be scared. It's just a mind experiment. Okay, but we're going to try to, I mean, we can go ahead and do the mathematical derivation of the Laplace domain, right? You can solve the integral, I can present you the integral and say, okay, this is the Laplace domain. I don't want to do that actually. I want to do it a little bit more practical. And therefore, we're going to do a kind of a mind experiment. So let's assume not a mind experiment, let's say an intuitive approach. That is how I named it. Let's assume we have this spring mass damper system, and we're going to think about a certain input, not a step, a sine wave. And we know from the second lecture, if I have a linear system and I'm exciting it with a sine, or cosine, you can also take a cosine, but let's stick for a sine. It has a certain frequency and it has a certain amplitude. The only thing what the linear system does is it changes the amplitude at the output and it changes the phase. It does not change the frequency, right? So when I excite a system with 10 Hertz, the output is still going to be 10 Hertz. However, it might have a different, the sine wave might have a different phase and amplitude. Okay? So now let's think about it and let's do this mind experiment for different sine waves, different amplitudes and different different frequencies basically, right? So for each frequency we get basically a change in amplitude and a change in phase. And now let's record this just for the sake of let's have some fun. Okay, so we said a linear system. For a linear system, a sinusoidal input signal u of t with a certain frequency results in a sinusoidal output signal with the same frequency but with a different amplitude and phase. Okay, let's write this down what that means. If we say u of t is equal, let's say an amplitude of 1, right? Sine, and we define a certain frequency, can be 10 Hertz, can be 100 Hertz. And let's say the phase shift is 0, right? So let's indicate this plus 0. So what a linear system does, and this only holds if the system is linear, you will get an output which has a certain amplitude. So the amplitude is going to change. It's still going to be a sine wave though. It's still going to be the same frequency, but it might have a different phase shift. Oops. I lost my pen here. So, right, so we might get some change in amplitude. So we move from 1 to A, and we might get some phase shift. Okay, so what can we do with this information? Well, we're going to think about it now. We're going to do this experiment for a lot of frequencies, right? So let's see and draw that into a plot and let's see what happens. Okay, so we say we take a system which might have here, what frequency do I have here? 0.1 radians per second, and we get a phase shift of 0 and an amplitude of 1, right? So the input is actually this guy here. And what we see here is the amplitude of y and the phase of y, right? So this is what's up there in the equation, what's this guy and this guy. Okay, so let's take a different frequency. Let's say we're going to take the frequency of 1. Here we might get a phase shift of, what's that, about 90 degrees, and we get double the output. Okay, let's do another one. Let's take a frequency of 2, and we get some more phase shift, and we get suddenly a smaller amplitude. So you should kind of realize where I'm heading to. I want to do this as often as possible, so we get a nice amplitude and phase distribution. So why is that now even helpful? Well, now we're going to think back, I think mathematical mass lecture 2 probably, that what we know is when we have a very complex signal, can be anything, we can actually do a Fourier series, right? We can decompose any signal in a lot of sine waves. I hope you kind of remember. If I have a step, I can compose this step signal with a lot of sine waves. Meaning that if I can decompose a signal always in a lot of sine waves, this plot should have a lot of information of our system there, right? Because it contains the information how a signal is going from the input to the output, right? So all the information, the information what our system is doing to our input signal now is in that plot. But now we only have 3 points, so there's not a lot of information there. So we need a lot of points, but we don't want to do this experiment in an infinite number of times, right? So now let's think about it, how we actually could approximate that line here, or these 2 lines, with a single function. So we have an amplitude distribution and we have a phase distribution. So how can we come up with a function which kind of has the information of the amplitude and the phase in it? So what do we need? What comes to your mind here? Could be a function of a real number, right? Or a real parameter. Is that enough? If I have a function which is just depending on time, for example, time is going to be a real positive number, so we're definitely not going to have a phase and amplitude information in there because it's just a real number. The phase cannot change. A real number always has a phase of 0, so this is not enough. What could be helpful is a complex number, because when I think of a complex number, for example 1 plus I, it has a certain phase and it has a certain amplitude, right? So this is why we're going to approximate that function with, or the distribution of amplitude and phase with a complex function. And this function we're going to name g of j omega. Okay, so let's do this on the next page. So we say, okay, our output y of omega, right? Clearly our output is depending on y, right? Because we have different frequency, we get different outputs. Is now composed of some function which is dependent on a complex number, j omega, times u omega, right? Or differently we could say, okay, this function simply describes how our input is related to the output, right? So that might look strange now, but this function here just basically gives you a continuous function for all of these points, right? So if you want to plot that, this guy here is g of j omega. This function now contains all the information for all the sine waves we want to experiment on. And if we are lucky, it's going to be kind of a continuous distribution. And now for each input, for each sine wave input, we know how this sine wave is transported to the output by our system, by our spring mass damper, for example, in terms of amplitude and phase, right? So why is this helpful? Well, we know that we can kind of decompose any signal into a lot of sine waves, right? So, and we have the information there how each sine wave is transported to the output. So, bottom line, this Gj omega contains a lot of information on sine waves, right? So the problem now is, well, a little bit of a problem is that sine waves unfortunately are not enough. Why? Because when you think of a decaying signal which goes down, this is not always easy to kind of reflect with a sine wave. So we need also exponential functions in there. And that's what we've seen when we solved ODEs, right? We talked about exponential growing or exponential decaying functions. So unfortunately, this Gj omega is not enough, and we have to think a little bit more. But that's going to happen on the next page. So many relevant finite functions, depending on time, can be transformed via the Fourier transformation. So we know that, right? In the so-called frequency domain. In system dynamics and control, however, non-finite functions are also relevant. So we need, for example, a sinusoidal or a step function, so which is not going to zero. And this is why we're gonna, instead of Gj omega, we're gonna extend that function by some sigma. And this is the famous Laplace transformation. So this would be your Fourier transformation, and this guy would, or it's not, it's your Fourier transformed, and this is the Laplace transformed. So if you want to think back into your mathematical lectures, you realize that the Fourier integral is just defined for decaying function, which are not decaying, for finite function. For example, funny thing, right? You have a sine wave, and you're not able to do a Fourier transformation of that sine wave because it's an infinite signal. This is just a mathematical, rule, right? However, in control system, we want to have both. We want to have decaying function and non-decaying functions, right? This is why we're actually going to move over to the Laplace domain. Okay, so this was the kind of background. I hope it's a little. I could present it to you a little bit intuitively. I know it's kind of, it takes some time to get processed in the brain, but you can always think of, instead of having a function of time, I want to think of frequencies which can decay or can be not decay, right? And this is what I'm doing basically when I move my system, which has all the information written in via a time function, to the Laplace domain, where we are basically thinking of frequencies, right? You might have learned in EE, in electrical engineering, about the Bode diagram. This is basically a similar concept. Okay, so again, now I'm going to show you how this transformation looks like for our spring mass damper system, and I'm just going to spoil the result, and we're going to discuss this in a little bit. Okay, so we said our system in the time domain looks like this. We have a damping term, and we have some kind of input. And in the Laplace domain, where we have g of s now instead of a function of t, the so-called transfer function is nothing but the ratio of the input to the output. And in this case, this function is ms squared plus ds plus 1. Okay, so you could say now, so what, right? So this is now a function, but a couple of things. We're going to learn how to derive that, and it's not that hard, right? The important stuff here is really this is equal, right? So the ODE has the same information in there what the transfer function has. It's just rewriting your system in a different form. But what you should note is that we have in the time domain, we have derivatives here, while in the Laplace domain, we only have a rational function. Rational, right, this way. I need to write a little bit nicer, I've heard. Only a rational, there's an O missing, rational function. Okay, so, and this is actually quite nice because we don't need to think about solving integrals anymore because we have the same information there just with a rational function. We don't have any derivatives, we don't have any integrals, it's just a rational function. It's just basically, yeah, it actually is quite, it's simpler. So you might raise the question now, what can I do with this function and how do we get there? And these are the things we're gonna need to answer next, right? How can we, first, how can we get to this rational function from our ODE? And secondly, what can we do with it and how can we do with it, right? So this is the part we're gonna discuss today and probably next time. Okay, so let's face the bottom line here. Yeah, okay, this is now written a little bit bad, but in your script it should be better. All relevant system responses and inputs now can be transformed into the Laplace domain, right? So it's really it's not a limitation, right? It's really an advantage because we moved away from that integral and differential equation now. And actually, everyone should be happy. Okay, so what are the advantages here in short? As I said, we have a single rational function which describes the input-output behavior of our system, right? And we will learn that actually only from that function we can extract a lot of information without solving any integrals, right? And this is a good thing. Well, the second point is, well, a lot of control engineering methods are defined in the Laplacian frequency domain. Why? Because it's much easier to handle than ODEs. And last but not least, and this is the important part for us here at this point, is that we actually move away from solving integrals to pure algebraic equations where we can simply use plus minus multiplications and division, right? And this is actually a pretty strong argument, right? Because you can get away with analyzing your system with this basic algebraic things and not solving an integral. So this is why I promised you will never need to solve an ODE on paper by ODE approaches, right? Because we're going to move over to the Laplace domain and things are a lot easier there. Okay, so finally, I've got one slide on a mathematical background. When you look up in your mathematical formula in textbook, they will always start with this mathematical background and how the Laplace transformation is defined. However, I think it's when you just give it to a student, it's kind of, yeah, for 98% it's kind of useless, right? So it's like, what does it mean? And this is why I try to give you the insight what this is actually doing. But you could also see that in the actual mathematical description. So what is the mathematical background? Well, if you open your mathematical formula, it would somehow look like this. Let's say you have an arbitrary function f of t. Let's start it this way, right? F of t. And you want to Laplace transform this guy here. Well, what you're doing is basically you're multiplying that function with some e to the sigma t times e to j omega t. And then okay, let's stop here for a second. What you are doing here is you're taking your signal in the time domain and you're multiplying, let's get rid of this for a second. You're multiplying it with this guy. And by this multiplication, you're basically analyzing what's the frequency content of your function f of t for a certain frequency, right? So see, this is the frequency omega here, and you're analyzing your system. What's the frequency content in here? Okay, and then you are summing all the contents up from 0 to infinity, right? So now we said, okay, only frequencies, only sine waves are not enough, and this is why we need to have some decaying function in there, right? So this guy here is basically a sine wave. This guy here is some exponential function, right? And now I'm analyzing my signal f of t for decaying function and for sine waves. Okay, and this gives my Laplace transform of that signal. So if we use basic math, we can simply rewrite this f of t, or this exponential function, in a way that we have minus sigma t minus j omega t here, dt. And now this guy here, let's do it this way, and it's actually working. And this guy is defined as your Laplace variable. So what we have now is the integral from 0 to infinity f of t e to the minus st dt. And this is what you will find in a lot of textbook. This is what the Laplace transform from a plain mathematical view is, right? But with this intuition, you're trying to decompose it, right? It's not really a decomposition, right? But I think it's kind of easier to visualize. Okay, so we have a question in the chat. I'm going to read it here. Where's our spring constant gone? Yes, I guess I missed it, right? Now when you're writing it here, right? Oh yeah, sorry for that. There's obviously a C missing here, right? And there's a C missing here. I'm just checking my script if I also did that wrong in here. Yeah. I think now it should be fine, right? C D times S. Yes. Thanks for the heads up here. As usual, it was just a test if everyone is listening still, also for the hard mathematical stuff here. Okay, thanks again. But yeah. So this is the mathematical background, right? And the summary basically is that we are assigning a complex function to our time function, right? So it's a one-on-one Laplace. It's a one-on-one transformation. It's just a different. It's just the signal is written in a different domain. Okay, this is basically what I just actually told you. So now you could say that's actually pretty hard, right? Because now you're telling us we can have signals, and now we need to transform all of those signals, and it's going to be horrible. Well, yes and no, right? Of course, if you think of a very strange signal, you might need to decompose it yourself. However, for our signals, what we like to use, right, step input and so on, there were smart people who already solved that integral for us. And that is why you actually can grab your mathematical formula. And if you find the right stuff here, somewhere here, you actually have the solution of a lot of signals in there already, right? So you don't need to solve that integral in our lecture, right? But there are some signals we should remember by heart, and this is what we are doing next. So bottom line is we don't need to solve for any dedicated signals, because we can look them up in our mathematical formula. You can even look at Wikipedia, you will find them, but as usually don't trust Wikipedia, so look at your mathematical formula. So one thing you could ask now is, okay, you're talking about signals, right? But we are actually interested in systems, because our spring mass damper is not a simple signal, it's a system. Well, yes, I give you that. However, we know that the transfer function is just the ratio of the input to the output signal. So if you know the input and the output signal, transform this, you also know the transfer function, so you know the system, right? Okay, so what we're doing next is we're gonna just now it's getting a little bit easier again. We are just going to take a look at the different signals, how they are looking in the Laplace domain. And these signals you will be already familiar with, right? So there's nothing new. We're talking about step, ramp, and maybe some exponential function. And then we're going to look them up in the mathematical formula and see how they look like. Okay. And then the interesting stuff here is that in the Laplace domain, we realize we don't need to solve any integrals, right? So this should be clear at this point. So, however, there should be an equivalent representation of an integral in the Laplace domain, but it's not an integral. So there are mathematical rules we have in the Laplace domain, and we're going to look at those. And actually, there's a strong connection between the signals and the rules, which I try to explain to you intuitively again. Okay, but let's start out with the signals here. Okay, signal tables, calculation rules, and block diagram algebra. Yeah. So, as I said, you can look them up and you will find a list of a lot of signals. And this time I'm going to start out with the exponential function. Well, in the time domain, this function looks like this, right? E to the power of at, right? I hope you agree with me. So in the Laplace domain, and your mathematical formula might use this sign here, this is usually implies the transformation from the time domain into the Laplace domain. And f of s, right? So you usually write that in a capital letters, and now it's a function of s, is nothing but the Laplace transformed of f of t, right? And if you looked it up, it is simply 1 over s minus a. So I hope this kind of rings. Well, no, it does not ring a bell yet. What you should realize is that this actually looks like the response, the time response of a PD1 system, right? Of a first order system. And we will see that this actually is how a first order system looks like in the Laplace domain. So there's some connection here. But yeah, for now, not important. This is just the transformation. Okay, let's take a look at our sine wave where we actually started. Well, the sine of, let's say, at, we have a certain amplitude. If you transform this guy, f of s is nothing but a over s squared plus a. So you don't need to remember those by heart, right? So this is just for a presentation how you would look it up in your formula. You can try after the lecture, say, okay, I want to actually make sure that this is correct. You could go into a mathematical formula and then check that, right? Just for fun. Next, we're going to do the impulse function, the step, and the ramp. And this is now really important, and this is what I expect everybody knows when we're working now with transfer function on the next slide. Because we are going to use it so often that, yeah, actually it will be hard to forget. So you agree with me that this guy here is an impulse function, and it's the Dirac impulse. The Dirac impulse is what we is the special case of the impulse function. And this is when you remember back or you rewatch the video I said when we talked about the impulse function, okay, there's a special case which is called Dirac impulse, which is basically has an area of 1 and goes to infinity. And I said we're going to need that later, this definition. Why? Because this Dirac impulse now can be Laplace transformed, and it results in the results I'm going to show you. So this is why we actually introduced it at this point. Okay, so we know in the time domain, f of t is equal our delta t, right? And remember, the delta t is has area of 1 and goes to infinity at t equals 0. Okay, if we transform this guy into the Laplace domain, it's simply 1. Okay, so far so good. Let's go to the step response, right? So we have a unit step, and we said, okay, this is sigma of t, which is basically implies that it is equal 1 for t bigger than 0, right? So this was our step. So if we actually Laplace transform this guy here, you'd end up with f of s is 1 over s. Okay. Next one, the ramp function, right? Here, our f of t is simply t times our step input. This is how we define it. So f of t is nothing but an explicit function of t times our step input, our unit step. So if we Laplace transform this guy, f of s is 1 over s squared. So why is this so important? Well, this is really a thing everybody should remember, and we will use it so often that there is no way you will not remember it, right? An impulse function is simply 1 times when you have an impulse which is not equal. Let's say you have an impulse input which is jumps up to 3 and goes down, then it's simply 3 in the Laplace domain. The step is 1 over s, and a ramp is 1 over s squared. So I hope you actually see already like a picture there where this is heading. We are basically going from here to here multiplied by 1 over s. Go from here by multiplied by 1 over s. We're going from here to here multiplied by s. We're going from here multiplied by s. Correct? Correct. So this was not very hard. But there's one thing now you should really, I mean, you can always learn it by heart, right? But I really like that explanation because it's so, it's very powerful and it's very intuitive. So we've seen, okay, Dirac, step, ramp, multiply, divide by s if you go in the one direction, multiply by s if you go in the other. So now let's go back to our signals. How do you get from here, from this step here to here? How do you get here? Well, I give you a couple of seconds to think about it. It's the same thing how you would get from here to here. If you mathematically, you can think graphically now, how would you compute the second function from the first function? Well, you need, I think the second one is easier. This guy here describes how the area here is propagating over time. So if you integrate this first function, you end up here. If you integrate this function here, you end up here. And remember, this has an area of 1. And this is, if this is the unit step, it's exactly 1, right? Okay, now let's go the other direction. Let's go from here to here. What you need to do is, well, this has a constant slope here, right? Slope is constant. So you basically differentiate that guy. And the same goes from here to here. This guy only has a slope here, which shows up at this time, at t equals 0. So this is again differentiating here. Okay, so far so good. And now you can connect those two ideas. Meaning that if you go from here to here, you integrate, and it's just a multiplication by 1 over s. If you go from here to upwards here, it's a differentiation. You multiply it by s. And these are basically the very important rules we can take away. Integrating a function in the time domain is equal to multiplying our signal by 1 over s. Differentiating a function in the time domain is multiplying our function in the Laplace domain by s. And you hope to agree with me that this is much easier than actually solving the integral or the differential function, right? It's just a multiplication by s or a division by s. Okay, this is basically summarized also on the next slide, step by step. In the time domain, you going from here, from the first graph to the second graph is an integration, and the same goes from going from the step to the ramp, right? In the Laplace domain, it's 1 over s and 1 over s. So if you want to go from here to here, let's say if you want to go from here to here, you need to integrate this function twice, or in the Laplace domain, you multiply it by 1 over s squared, right? And again, I hope you agree with me that this is much easier. The same holds for going backwards, right? So if you want to go from here to here, you need to differentiate that twice, right? Or multiply it by s squared. Okay, so let's sum up where we are. We know how to transfer signals. We know we don't need to because some smart people already did that for us, so we just look it up. And based on these signals, and I told you we're mostly going to stick to an impulse, a step, a ramp, sometimes a sine wave, we can actually kind of really intuitively derive some calculation rules, integration and differentiation. But the original motivation was, and this is the last part from the rule side, before we gonna take a look at a small example, is the convolutional integral, right? So remember, this was the original motivation I gave you. I said, if you have a system and you want to know what the output is to a given input, you need to solve the ODE. If you don't know the input and you just want the input, let be u of t, so an arbitrary function, you will end up with the convolutional integral. And it's going to get nasty, right? For each different signal, we're going to solve this convolutional integral. So the question now is, okay, this was the motivation why we moved over to the Laplace domain. So now what? So what's the message here? How is the convolutional integral, the Faltungsintegral, now looking in the Laplace domain? So where's the strengths now we can use? And that's what we're going to look on the next slide. So the convolutional integral, if you have two signals, right, looks like this. And this guy here shows up when you solve an ODE for an arbitrary signal. So this is the connection here, right? In the Laplace domain, this is a simple multiplication, right? So instead of solving the convolutional integral, what you can do is you can actually transform your two signals and then multiply them together, right? So instead of solving that very complex integral, which has an f of t minus tau times g of tau, you can actually take these two signals and just bring them over to the Laplace domain and multiply it together. And actually, this was one of the main motivations 50 years ago, also to introduce the Laplace domain, because you avoid the step of solving your ODE. You took your ODE of your system, and your ODE has, what has your ODE? It has y dot, u dot in there. You transform all the signals into the Laplace domain, and then you have your system there, and then from that point of view, you transform it back, and these two transformations give you also the result of the ODE without solving a single integral. This is not a strong argument nowadays anymore because we have a numerical solver solving our ODEs. But this, when you read books, you will always hear that argument. I don't think it's really that valid anymore, because we can solve ODEs numerically pretty fast without. But the original motivation, or one of the original motivation, was that really solving ODEs, it's much easier to do via the Laplace domain and the transformations, and not with the in the time domain. So for us, however, important is what does this convolutional calculation rule actually mean now? And now I hope I can close the circle here, because all this block diagram algebra, right? I've shown you a block diagram already in the first lecture where I said, okay, we have a block there, and there goes a signal in, and the block is a system, and the system transports that signal to an output. This is actually the basis for this is actually the Laplace domain, because now it's not solving an integral anymore. It's basically multiplying things together. Okay, let me show you what I mean with that. When you have an ODE, let's say a block diagram, right? And I always said, okay, we have a signal U which goes in there, and we have something which comes out there. And in reality, what is in there is the ODE, right? And your ODE is something like, y dot of plus y of u. So this is not really something intuitively, right? However, in the Laplace domain, you have your transfer function in there of your g of s, and now you say, okay, my input goes in and my output goes out. In the ODE case, you need to solve the convolutional integral. In the transfer function case, you need to multiply those things together. So in the transfer function case, you simply can say y is g times u. And this is actually why you draw all in controls always block diagrams, because it's the basis here is the convolutional integral rule, because we are allowed now to really write our output is the input multiplied with the output in the Laplace domain, not in the time domain. In the time domain, it's this guy here. There's no multiplication in there, right? So, and this is why, sorry for that, let's get rid of this. This is why we actually can get away with this block diagram algebra. If we have a very complex system, and you're all aircraft engineers, right? An aircraft like this guy here has a lot of actuators, 20 actuators steering all the surfaces. That would mean if you want to solve the input from the pilot to the output of the aircraft, you would end up with a convolutional integral which has 20 integrals in there. Nobody wants to solve that, right? In the Laplace domain, you just multiply all these together, right? So you can, very complex system, for example, think of our bathtub last time, right? It had a bathtub, it had a pump, it had a motor. If you had time domain equations, you would end up with a convolutional integral with 3 integrals, right? If you don't define your input. And you need to solve one by one after each other. Well, only 2 because one system was constant. Okay. However, if we now want to go into the Laplace domain, we can actually just multiply all these things together. And this is where the strength of the Laplace domain is, right? When we have an aircraft, we have an actuator, we have a pilot, which could also be an ODE. And we want to know is what, as an engineer, we're interested in from the output to the very from the input to the very last output, right? We can multiply the subsystems together. Okay, what I mean with that, I will show you an example on the next page, because I know it's kind of, not that easy. Okay, let's assume we have our spring mass damper, but we are lazy and say we don't want to apply the force by ourselves. We want to use an actuator here. And instead of applying the force directly to our mass, we're going to use some current, for example, or a voltage, whatever you like, which we're commanding to this actuator, right? So what's happening here is I apply a current command, my actuator, my cylinder is moving, and it's moving the mass, right? So instead of myself moving this guy, we are just applying a current, and this guy moves. So it's just an academic example, but I want to show you what's happening. So as an engineer, we are ultimately interested in how much movement of the mass results from our current, right? So we plug in a current, could be a step, and then we want to see where's our mass moving. So that's what we are interested in. We are probably not interested about the flexibility of the actuator and so on, right? We want to just know where's our mass going. Okay, so two options here. We could describe those systems by differential equations. Okay, let's do this. Let's say, okay, we know this equation now. We know, okay, our spring mass damper, and this is just the spring mass damper system. Sorry, spring mass damper system without the actuator kind of looks like this, right? Second order system, nothing special there. Well, but this time we have a second ODE, right? So we have this first order actuator, which is basically this one here, right? So how would you solve this? And the clue here is now we don't want to know it's for a certain input. We don't define it's going to be a step, it's going to be an impulse. It can be anything at this point. Okay, how would you solve this? Okay, first possible solution, solve the second ODE, right? So we solve this guy. We get out our u of t, and then we're going to insert that into our first ODE and solve solve the first one. However, if we don't solve it, right, for solving this ODE, we need to define our input. Say, okay, input can be anything, just leave it there. You're ending up with a double nested convolutional integral. And always when you define this, your input, you will need to solve the double integral. Not that nice, right? So let's consider another option. Okay, in the Laplace domain, we're going to transform these two systems. We're going to learn how we're going to do this next time. And then we know, okay, it's going to end up with a convolutional integral, but convolution, eine Faltung, it's only a multiplication in the Laplace domain. Okay, that's actually easy. So let's take our spring mass damper system, multiply it with the actuator, and that's it. And now we have the solution for y. So for this, for our output, for any input, right? So u of s now can be anything, right? And we have y here and not y dot or an integral or something. We simply have y here. And I hope you agree with me that this is much easier. Okay? And this is basically the idea of this, why we actually, well, to be honest, control engineers are sometimes lazy and we don't want to write down all these long equations. We like to draw block diagrams, right? And this is why we are actually allowed to draw block diagrams and really think of, if you see a block diagram, it's really taking the system and multiply it with the input, and this leads to the output, but not in the time domain, in the Laplace domain, right? This is, as I said, the foundation of this, or the basic idea why we are allowed to use block diagrams. And this is what we're going to do next. We're going to discuss a little bit some rules on this block diagram algebra. We have used it already, but we didn't set up the rules. And this is what we're going to do now. Okay. So it's basically a pictorial representation of a lot of systems, right? So this, for example, is a series connection. So each of these guys here is a system. So we got three systems. This is our input signal. And when I say signal, it's in the Laplace domain, and this is our output. So how would you determine now here the output y? So remember, if this is in the Laplace domain here, in the time domain, sorry, you would have three systems and you would need to solve each ODE. In the Laplace domain, it's just multiplying those things together. Okay, so our here our y of s is nothing but Fi plus 1. So you always start from the back, right? Because you want to know the output, not the input. Times Fi times Fi minus 1 times U of S, right? And now this is our new system, which we call f of s. Well, and this f of s is nothing but we multiply all the individual f's together, right? Okay, this is a series connection, and this is what you will find very often. What you also will find is a parallel connection, and now we are introducing this guy here and this guy here. And whenever you see that thing here, this is basically a summation. Let's write it down. Summation. And remember, you already used that summation actually when we draw block diagrams for a control loop, right? We said we're going to feedback something and we're going to subtract it. This is already where we used it, but I didn't explain it to you what it actually is. Okay, so what do we have here? Well, here we have our y of s is nothing but the first guy, and as this is a summation, it's plus the next one, right, times u of s. And this now here is our new system f of s. And if you have this parallel connection, we are actually having just a summation of all the parallel systems, obviously of s. So what you should take away here is really this summation, this guy here, and this is basically, you actually don't need to draw this, because what it tells you is that this guy here is moving, the signal is moving here and it's moving here, right? So it's split up. So this is, you could say this is a split. Often in the literature, the split is not even drawn, right? But yeah, the important stuff here is the summation. Okay, so let's go a little bit further and do some examples with this, some very basic examples, and I will let you answer the examples in the chat. So let's try to do relocation of systems. So okay, we have this guy here, and what we do have is y is equal. So we move from here, right? Here we have a multiplication, so it's f1 times. Now we got a summation, right? Remember, this guy is a summation here. And here we're going to sum up u1 plus f2 times u2. Okay? So now let's try to relocate it, and I let you think for a second. Let's say if we have our input u1, and we are moving this guy to here. This is also a nice thing, right? We can just move systems around. Obviously, we still have a block here, which needs to go through U2. So what, I let you answer that in the chat, what goes in here now? Anybody has an idea? Obviously, if we relocate something, the equation here is not allowed to change, right? So this equation should still be the same. So let's write here what we get. Y is equal, we are here, we're still directly coming to the summation. We have f1 times u1, f1 times, yes, correct, right? So if we want to, what's happening is this signal is moving through here and this signal is moving through here. So both signals are multiplied by f1. So if we move this guy here forward, actually our second signal misses this pass-through f1, right? And this is why we need to plug it in here. Okay, and if you now write f1 times f2 times u2, you should figure that this now is the same, right? Check. Okay, so what do we have here? Here we have y1 is equal f1 times u1, and here we have our second output is nothing but taking the input times f2. Okay, so if we now want to relocate our f1 to the front, what should be in here for our y2? Remember, the equation should stay the same. So what do we have now? We have y1 is equal to f1 times u. So this is actually the same. So we did a good job there. But what here we would have, yes, exactly. Here we would have now f1, right? And obviously we should not have f1 here, so we need to multiply by 1 over f1 and f2. So in this case, it would stay the same. So what needs to go in here is this guy, right? f2 over f1. Perfect. So these are basic rules, and you actually will use them often, and I will upload a couple of examples after that lecture so you can practice. There's one piece missing at this point. One addition to this block diagram algebra. We know now series connection, parallel connections, we can move around, we know what a summation is. There's one, well, it's not really an additional point, you can actually derive it from what we have already learned here with these block diagrams. It's the feedback loop, right? Because in control, I said we're always going to measure something and we're going to feed it back, like you probably do in the second practical exercise with the espresso machine. You're sorry. You're taking your measured temperature, you're feeding it back, you're subtracting it from the desired value. So we're going to draw this on the next page. So, and this is a classical feedback path, right? So you take your output signal, you feed it back. So this is really the definition of a control loop, of a closed loop control loop. Remember, if you don't have this, you're open loop control. You're doing basically Steuerung in German, not a Regelung. Okay, still, we want to know what's our y here, independence of our u. Okay, let's apply what we have learned so far. Well, if we go here, our y is g of s, then we are here. Next thing we pass through is our r of s, right? So we are here. So what's next? Well, next is a summation, right? The summation is u, and now I've indicated both here, right? Plus, minus. Let's change the color here because this is important. And when you go back, okay, what's actually here is also y, right? Because we are taking that y and we are feeding it back. Okay. Okay. So now we have all we need, right? Because we have our output y here and we have the input. There's nothing else dependent on, right? So now we can do the transformation. Okay, we say y is, and now we actually changing the signs, right? If you multiply that out, bring it to the other side, the sign is actually changing here. Plus minus g of s times r of s times y is equal g of s times r of s times u. Okay, now exclude y and divide it through, and you get y is equal g of s r of s 1 minus plus G of S R of S times U. Okay. Of S of obviously, but I'm just skipping this. Okay. And this is what we call a classical feedback loop. And this is why we have G and R here. G would be your system, and R would be the controller, the regulator, whatever you like to name it. Regler, this is why it's R. Okay. Okay, so you have a system, you have an output, you measure something, you feed it back, you compare it, and then you feed it through your controller, right? Really important to note here is that if this here is plus, it gets a minus in this loop, and if it's a minus, it ends up being plus here, right? Okay, let's do another loop where we say, okay, we have the second system in here. It could be a sensor, for example, or it could be a controller which is acting here. Same strategy, right? Y is equal G of S, we're here, times, we have the summation, U plus minus R of S times Y. Okay, then if you bring that to the other side, exclude it, you will end up with G of S 1 minus plus R of S times G of S times U. You can do it slowly if you want, but yeah, it's always the same idea. Really just multiplication. And remember, what's really actually awesome is here that R of S and G of S are systems. They are described by ODEs, but we're still just taking them and multiplying that. Think of, you are not allowed to do this in the time domain. In the time domain, you would have an ODE with y dot plus y. You are not allowed to take that ODE and just multiply it to a second ODE. That will go wrong. Here, you can transform that ODE, and we will learn how, and then just multiply all these systems together, and you end up with a new system, which is just this function here. Okay, we've got a couple of minutes left. I think I have 3 slides, and I'm going to finish with these 3 slides, I think, because then you can do the exercises with the block diagrams in the afternoon, for example. Okay, let's take this loop here, and now we don't have this output y at the end. We have e. Could be the control error. Okay, how you want to compute E now? Okay, you can say same thing as before. E is equal U plus minus, and you go back. And let's assume this is Y. Now you are screwed here, right? Because you have 3 variables, U, E, and Y, but you're interested in the system from U to E. Okay. That only means that you need to go further, right? So what's y here? Well, y here is nothing but G times R times E, right? So y is nothing but this here. So you go further back until you reach here. Now you only have 2 variables in here. Okay. So if you bring it to the other side, you multiply it out, you end up with 1 minus plus G of S times R of S. Okay, I mean, you can write the function of S here, right? But I just omitted this for the sake of space times U. Okay, this is what you have given here. And now to get that clear, you can always do the computation slowly as you want. Sometimes, though, you need to shift things around. This is why I've shown you this, shifting it forward, shifting it backward. This is what you do sometimes to make the picture a little bit easier. You will see that when you do the examples. However, there's also a short version of it where you don't need 3 lines, you only need 1 line. I usually tell the students, go with the slow version first and then double check with the fast version, because the fast version, if you're not used to it, could be prone to failure But if you get used to it, it's actually pretty fast. So I name it calculation trick. The calculation trick is always you go, and this only works for a single isolated loop. What's a single isolated loop? Well, this is only one feedback loop, right? In all these examples, you only have one loop, right? This is what I mean with a single loop. When it doesn't work, it would be, for example, something like this. G1, G2, this would not be a single isolated loop. Here you would have two nested loops. Then you need to shift around, right? So just to get that clear what this means, right? So only when you can identify a single feedback loop, this is usually a good thing to do. You simply go direct and you go 1 minus plus the loop. Okay, what does that mean? Okay, that means, change the color, direct, you go from your input to the output directly, it's just a 1. And you go 1 and you change the sign, right? So if you have plus minus here, you do minus plus, and then you go through the loop. And the loop is R times G. And you see this is the same thing. Okay, let's go back and let's do it here. We're going directly from here to here. It's R times G over 1 minus plus the loop is again R times G. You should see it's the same. Here we're going U to Y. It's G of S directly over 1 minus plus going through the loop is again R times G. See, it's the same. Again, it takes some time, but you will get used to it. So I have a final example, and I'm going to do this, and then we can close the lecture, and I will then upload the examples. This guy here basically has now 3 systems, right? So we have 3 systems. And we have 2 inputs, U and D, and we have 1 output. And we want to now know the output Y depending on 2 inputs. Okay. You can do it slowly. Okay, let's do it slowly. I would say, okay, Y of S is equal. We're going through G, then we come to a summation, D plus R, we're here, plus minus, sorry, not R, another bracket, U plus minus G of S times Y. Right? So we bring that to the other side, we multiply it out, we end up with, let's see, that must be G over 1 minus plus G R G S. I'm omitting the dependence on S, right? Times D of S plus, and what do we have here? We must have R of S times, well, let's just write R times G over 1 minus plus G times R times GS times U of S. So if you want to do the calculation trick, it will also work. If you go directly from here to here, it's going to be G. If you go directly from here to here, it's going to be R times G. And the loop is always R times G times GS. It's always this guy. Right? This is the introduction for the block diagrams, as promised. I will upload a couple of examples so you can practice. And yeah, I will probably, I will upload them, and then we will do next week at the beginning two more examples, just to get a little bit of insight. Okay, one last slide for today. What we have, just want to sum up what we've done today. So instead of having an ODE, an integral function, we simply have now a rational function without actually solving the ODE. And this rational function has all the information in there from of the input-output behavior. And remember, at the beginning, when we talked about systems, we said as an engineer, we are mostly interested in that input-output behavior. What do we send in? What do we get out? Right. So all the information is now covered, not in an ODE, but in a rational function where we can apply simple mathematical techniques and don't need to even solve an integral. Our life is actually even getting more simpler because we don't need to do the transformation by ourselves, right? We just take a look at our mathematical formula and everything is in there what we need. And based on all of that, we derived the so-called block diagram algebra. So for very complex systems, which could be decomposed of a lot of subsystems, where each subsystem is described by an ODE, which is going to be horrible to solve, we can transfer all these ODEs to the Laplace domain and we simply multiply it together. And this is the basic idea of this graphical display, the so-called block diagram algebra. And the matter of fact is, when you look at aircraft systems, right, complex aircraft systems, they are actually, for control engineers, you will get a big picture, no ODEs there, you will get a lot of different blocks, and in each block there is somewhere hidden an ODE or a transfer function. But I think the X31 control system is like an A2, A1 sheet of paper with a lot of these systems in there, and each system is like has some information in there, but you are able to display this whole complex thing with this very graphical, illustrative manner without actually writing all the ODEs there. So it's a good overview, right? So what's missing? Well, this is one thing, right? We need to know how to transform our differential equation to a transfer function, and then we need to extract properties, because this was the original idea, right? We said, okay, we're going to move over to the Laplace domain, and we're going to analyze this function, and we're going to analyze it without solving the integral and so on. And this is what we're going to do next time. And I will show you how to get from the ODE to the transfer function. You could say now, why didn't you show us this right at the beginning? Well, because you only need a simple calculation rule, one calculation rule out of the rules we just derived, because the Laplace domain is not only for system, right? It's basically a mathematical tool, and I rather come from the perspective, what is the Laplace domain doing to signals, to systems? If you understand that, the transformation is actually a piece of cake, right? It's really easy. You only need one single rule and you need to do some division and you get to the transfer function. This is really the cheap part here. And then we're going to learn next time how we analyze a system without solving ODEs. We will get out a lot of information on our system responses by just looking at or analyzing our transfer function. Stay safe, stay healthy, and have a good rest of the week. Bye-bye.